There are several different types of fuels that can be used in rockets, each with their own unique properties and efficiencies. They can come in all forms of matter, whether it be solids, liquids, gases, or even in plasma. Today we'll be discussing the chemistry that goes into literal rocket science. There are several different categories of solid propellant rockets. These include black powder or gunpowder propellants, zinc sulfur propellants or ZS, candy propellants, double base propellants, composite propellants, high energy composite propellants or HEC propellants, composite modified double base propellants, smokeless propellants, and electric solid propellants. For simplicity, the types that will be elaborated upon will be zinc sulfur, double base, and composite propellants. Zinc sulfur propellants were a commonly used propellant for experiment. This powder, also known as micrograin, is consisted of a mixture of 2.04 parts zinc to 1 part sulfur by weight. Although this flames can reach a staggering 2,600 degrees Fahrenheit or about 1,427 Celsius and has an effective exhaust velocity of 1,490 feet per second, because it is difficult to compress the powder to a consistent value, rocket motors made with this formula typically either don't have much power and may not get off the launch pad, or they blow up from overpressurization. Another type of solid propellant is the double base, which are used in anti-tank rockets or missiles and in some tactical missiles. Their main advantage is that they produce a minimum amount of smoke when used. These contain mostly nitroglycerin and nitrocellulose, which can be rolled or extruded, mixed, casted, cross-linked, and the grain case bonded. On the right is the structure of a nitroglycerin molecule. There are several different composite propellants, such as ones based on ammonium perchlorate and ones based on nitramines and an active binder. They are considered to be a propellant where the oxidizer and the fuel are intimately mixed together. One common major problem that comes up in the usage of this type of rocket is its brittleness. These types of propellant have the potential to create cracks and overpressurization of the motor due to increased burn area and catastrophic failure. Here is the process of the manufacturing process of a composite propellant. Solid propellants have their own advantages and disadvantages. Solid propellant rockets are much easier to store and handle than liquid propellant rockets. High propellant density makes for compact size as well. At the same time, relative to liquid fuel rockets, solid fuel rockets have a lower specific impulse, a measure of propellant efficiency.
The second method is plasma-propelled rockets. There are two different major builds of plasma rockets that function similar. The first one is the HDLT, or the Helicon Double Layer Thruster. This prototype rocket is currently being tested in a facility in a lab called Wombat XL in Australia. It is propelled by high-velocity ionized gas that shoots out of the exhaust to create thrust. The way this works is multiple different kinds of gases are injected into a tubular chamber with one open end. There is a radio frequency emitted from an antenna on the rocket. The electromagnetic wave emitted from this is used to break down the gas into a form of plasma, which is where the plasma comes from. The term helicon is described as low-frequency waves that are well known because of their insensitivity to variation in plasma density and magnetic field. These excite the plasma even more, which produced more heat. Because of this interaction between these things, a solenoid, basically a coil that is used to create a magnetic field, is used to keep a semi-constant charge around the tube. Near the source of the engine, there is more electrical potential, better known as voltage. This is to make sure that all the charged particles go where they need to go so that the overall charge by the exhaust is close to neutral. Because this form of propulsion is not very burst heavy and is more like thrust over time, it has very long self-sustained but lacks initial takeoff speed. So far, the most efficient proposed purpose for this rocket on this type of rocket is on satellite keeping, low Earth orbit, and deep space uses. It has an average lifespan of about 50 years. One of the biggest upsides to using an engine like this is that because it doesn't need to carry as much propellant as a traditional rocket, it is said to be able to cut down up to 1,000 pounds or 454 kilograms on launch weight, making it easier for longer travel and escaping the Earth's gravitational pull, according to HDLT applications from the Plasma Research Laboratory. The second type of rocket is similar to the previous, the Variable Specific Impulse Magnetic Plasma Rocket, or VAS-IMR. According to the principal VAS-IMR results and present objectives, the propellant, a neutral gas such as argon or xenon, is injected into a hollow cylinder surfaced with electromagnets. On entering the engine, the gas is first heated to a cold plasma by a Helicon RF antenna, also known as coupler that bombards the gas with electromagnetic waves, stripping electrons off the propellant atoms and producing a plasma of ions and loose electrons that flow down the engine compartment. By varying the amount of energy dedicated to the RF heating and the amount of propellant delivered for plasma generation, VAS-IMR is capable of generating either low-thrust, high-specific impulse exhaust or relatively high-thrust, low-specific impulse exhaust. The second phase of the engine is strong electromagnet position to encompass the ionized plasma in a similar fashion to a nozzle that compresses gas in a traditional rocket engines, followed by what is known as the ion cyclotron heating (ICH) section, emits electromagnetic waves in resonance with the orbit of ions and electrons as they travel through the engine. Resonance is achieved through a reduction of magnetic field in this portion of the engine that slows the orbital movement of the plasma particles. This section further heats the plasma to greater than 1 million Kelvin, about 173 times the temperature of the sun's surface. As stated by Star Power from Air and Space Smithsonian, then finally it is launched out of the end to create thrust. This can create velocities up to 500,000 meters per second. Although this has many advantages that are similar to that of the HDLT, it also has some similar disadvantages. Because of the use of superpowered magnets, it has a difficult time interacting with other strong magnetic fields. Another glaring issue is with heat management. With all the processes and heating going on to create the plasma, it would have nowhere to go, so we would have to find a way to effectively dispel it. The magnets could also have conflict with other onboard computers and similar machines. If we could find a way to produce these types of rockets effectively and find a way to reduce the downsides as much as possible, these could be the next step in space travel and space technology.
The last method we are talking about is the liquid fuel engine. The engine and chemistry behind this are fairly simple. The engine requires a propellant and an oxidizer. Most commonly, they will use liquid hydrogen and liquid oxygen. This would be kept in separate chambers until they were flooded into a tank directly above the engines, where they will be combined and ignited, sending the exhaust out the engine to propel the craft forward. This reaction can be modeled by the chemical equation H2O true. Through heat yields H2O plus 1/2 oxygen 2 and heat. As you can see, there's a wide variety of possible rocket types that can be used in the future, but finding the most effective one will be difficult and expensive. So far from this, we have solid propulsion, liquid propulsion, and plasma propulsion. Only time will tell which one of these comes out on top.